me begin by repeating what I said in the last lecture, namely that this real analysis is a very important and very basic course, and the concepts that you will learn in this course will be quite useful in many other courses in mathematics, like complex analysis and functional analysis and topology, differential equations, and several other courses, not only in mathematics but even outside also. And also this is one of the courses which gives importance to proofs. Okay. Proofs of various theorems will be discussed in the course, and so the logical reasoning that you will learn while giving those proofs will be quite useful in mathematics and also outside mathematics in life. Okay. So we were discussing in the last class certain aspects about the functions. We were revising some concepts of the functions. So let me again briefly say a few things. Now to begin with, let us say that x and y are two non-empty sets, okay, and suppose f from x to y is a function, okay. Then given any subset A of x, we can talk of what is meant by image of A, that is f of A. This will be a subset of y, okay, this will be a subset of y, okay, and so this is nothing but set of all elements of the form fx for x in A, okay. And alternate way of describing this will be it set of all elements y in B such that there exists x in A such that fx is equal to y, okay. Something like this we have seen. Similarly, if we take a set say B in Y, okay, we can talk of what is meant by inverse image, okay, that is let us just take, suppose this is the set x and let us say this is the set y, and you have this function f. Now if we take a set, some set A here, its image is in y, so this we will call image of f, image of A under f, image of A under f, okay. Similarly, if we take some set, let us say B here, suppose this is B, then we can talk of what is meant by its inverse image here, okay, its inverse image, and so that we shall denote by f inverse of B, okay. So what is f inverse of B? It is the set of all those x in x such that fx is in B, okay. So set of all x in x such that f of x belongs to B, okay. So this is a subset of x, just as this is a subset of y, okay. Set operations like unions, intersections, etc., inverse images behave in a better way than these direct images, okay? So since these are elementary set theoretic properties, I shall not go into the proofs of those, I shall leave those two things to you as exercises, okay. So what are the properties that I am talking about? They are this is the properties, okay. Like for example, we want to ask some very elementary questions, like suppose I take, say, instead of just taking one set A here, suppose I take say two sets A1 and A2, okay, and then take A1 union A2, then the corresponding images will be FA1 and FA2, okay. Then how is FA1 union A2 related to f of A1 union A2, okay. So that is a kind of question, and as we have seen yesterday, then why just restrict to 2 or 3 or any finite family, okay. We can talk of any family of sets, okay. And so what we will do is that I shall let us say that AI is that suffix small I belonging to big I, let us say this is a family of subsets of X, family of subsets of X, so where this big I is an indexing set, something that we discussed yesterday, okay. And similarly, let us say B suffix small z belonging to big Z, this is family of subsets of Y, okay. Then properties that I have in mind are the following. Let me just state some of these properties. So let us say first property is image of the union f of union ai, I belonging to I, this is same as union f of I belonging to I. Okay, this is an elementary set theory, so I will give this to you as an exercise. Okay, try to prove it on your own. Okay. All right. When it comes to intersection, we don't have such a good relationship. Okay, there is f of intersection ai, I belonging to I. You might expect that that is also equal to intersection of f ai, but that is not true. Okay, so this is only, we can only say that this is contained in intersection of f of ai, intersection of f of ai, I belonging to I. Okay, right, and this inclusion can be proper. Okay, you can find examples of a function and these sets. Okay, so that f of intersection of the sets is not same as intersection of the images. Okay, so I will give that also to you as an exercise. Okay, so give an example to show that the above inclusion can be proper. Okay, what does that mean? Okay, that is, you find a family of, just find an example of x and y and f and a family of subsets of x such that this is properly contained in this. Okay, and I will give you a hint. Though here I have said arbitrary family, you can just get an example of two subsets. Okay, two subsets. Then, though I don't state here as an exercise, I will ask you one more thing to do. Under certain conditions on f, this becomes equality. Okay, under certain conditions of f. Okay, and we have discussed some of the extra properties that f may or may not have, like 1 1 on 2, etc. Okay, I will not say which exactly the condition. Okay, you try to find out on your own that under an extra condition on f, this becomes an equality. Okay, what is that condition? Okay, try to find out on your own. Okay. All right, now coming back to what I said earlier, that inverse images behave better way in this respect, and there you don't have this kind of problem. Okay, so third property is that, suppose I take this family of subsets of y and take their inverse images, then f inverse of union bj, j in j, this is same as union f inverse bj, small j belonging to big J, and the same thing is true about the intersections also. Inverse image of intersection of any family, this is same as intersection over small j belongs to f inverse bj. Okay, so compare this property 4 with property 2, and that is the meaning of saying that inverse images behave in a better way. Okay. Right. And there is also one more property, that inverse image of a complement is also same as the complement of the inverse image. Okay, that is f inverse of a complement, remember a complements means x minus a. Okay, x minus a. Okay, this is same as not a complement, it should be, because inverse image for that it should be a subset of y. Okay, a's are subsets of a, so let us say b complement, this is same as f inverse b is complement of this whole thing. Okay. Okay, so that is about the elementary properties of functions and how the sets and their unions behave with respect to direct images and the inverse images. Okay. Now let me go to another important concept in this review of elementary set theory, namely relations. We can similarly take two non-empty sets x and y and talk about, let us say, a relation R between x and y. Okay. Just as function is a rule which assigns every element in x and element in y, similarly relation is also a rule, okay, which assigns elements in x to elements in y, but there is a difference. Okay, what is the difference? In the functions, every element has to have some image. Okay, every element has to have some element, whereas in relation that is not the case. Okay, some elements may have some image or some elements may not have image. Okay, all right. One more thing, in case of function, every element has a unique image. It cannot happen that the same element goes to two different elements. Okay, but again that is also not required for the relations. Okay, any number of elements can be attached to any number of elements. Okay, so usual way of denoting that is that we say that we use this symbol. Let us suppose small x is in x and small y is in y. We write this x r x, x r y. Okay, x r y. Okay, this is read as saying that x is related to y under the relation R. Okay, so this is, we read this as saying that x is related to y, x is related to y under R. And you have seen so many examples of relations in your several of the undergraduate courses. So again we will not go into very detailed properties of relations and all that, but let us, we need a few things in our course and we shall quickly revise those. Okay. Among various relations that we are going to consider, one of the important class of relations comes when x is same as y. Okay, that is relations on the same set. Okay, so such a thing is called relation on x. Okay, now before going to that, let me also mention one more thing. With each such relation you can associate a subset of x cross y. Okay, and usually that set is also denoted as by the same symbol R. Okay, so what I can say is that suppose you collect a set of all xy in this x cross y such that x is x r y, that is x is related to y under the relation R. Okay, suppose you collect all such pairs xy which are related to each other under the relation R, then that gives a subset of x cross y. Okay, that gives a subset of x cross y. Similarly, if you are given any subset of x cross y, you can define the relation. Okay, just pick up those pairs and say that those pairs are related under the relation, and that is why one can say that there is no difference between a relation and a subset of x cross y. Okay, right, every relation is a subset of x cross y, and that is why that is usually taken as a definition of a relation. Okay, a relation is a subset of x, so subset of x cross y, and that is why we denote this also as R. Okay, denote this also as R. Okay, so one of the ways of defining a relation is just give a subset of x cross y that defines a relation from x to y. Okay, so when, let me go to the next case, when y is equal to x, we call this as relation on x. Okay, relation on x, instead of saying relation between x and y or relation between x and x, we say relation on x, and so this will be a subset of x cross x. Okay, this will be a subset of x cross x. Okay, now such a relation on a set x has some very interesting property, has in the sense we can discuss some very interesting properties of such relations. Relations may or may not have this property, but the properties themselves are quite interesting. So let me just begin with those properties. Okay. Of course you may have come across these properties earlier, but since we need these properties quite often, we will take a quick review of this. Okay. So let us say that R is a relation on x. then we shall first define what these properties are and what is meant by this. Okay, we will say that R is said to be the first property, as you would have heard of, I am sure, reflexive. If R is said to be reflexive, yeah, now tell me what is meant by that. Yeah, each element is related to itself, okay, under the relation. Okay, so R is said to be reflexive if we say x R x for every x in x. Okay, x R x for every x in x. Okay, all right. Then second property is, yeah, symmetric. If repeat that, x related to y and
y related to x.
This happens for every x and y.
No.
Yes.
Yes.
Right. If x is related to y, then y is related to x. Right. Neither things may be true. Okay. X may or not be related to y, but what we want is that if x is related to y, then y must be related to x. Okay. So if we should say that x or y implies, right, you understand this implies means if then. Okay, okay, this is if x or y then y or x. Okay, if x or y then y or x for every x y in x. Okay, right, okay, right, all right. Then the third property, which transitive. Okay, R is said to be transitive if, yes, then
X related to z.
fine, okay. So if x, you take x related to y and y is related to z, this should imply x is related to z for whatever three elements you take, x, y, z in x. Okay, of course I am not saying here that this x, y and z must be distinct. Okay, two or three of them may coincide, but that becomes a trivial case. Okay, right, okay, all right. Then one more thing. Okay, let us call it what is called antisymmetric. Okay, what is this? Right. Okay, so antisymmetric is something that is exactly opposite to symmetric. Okay, right, exactly opposite to, say what does symmetric say, that if x is related to y then y must be related to x. Okay, and antisymmetric means this can never happen, but of course if it is a reflex relation, x is related to itself. Okay, so this is the only way in which it can happen, x is related to x. So what it means is that if x is related to y and y is also related to x, this means x is equal to y. This should happen for every x y in x. Okay, this should happen for every x y in x. Okay, and now since we are discussing these properties, let us also recall one more very important types of relation. Okay, so let me just remind you, that is R is said to be an equivalence relation. Equivalence relation. Okay, equivalence relation if R is reflexive, symmetric and transitive. Okay, if R is reflexive, okay, I will simply write reflexive, symmetric and transitive. Okay, all right. Then one more thing. Okay, R is said to be a partial order. What is partial order? Yeah, instead of symmetric, that is replaced by antisymmetric, okay? Reflexive, antisymmetric and transitive, okay? R is if R is reflexive, antisymmetric and transitive. Okay, I am sure you have heard of these terms earlier. Okay, just to fix the concepts, let us see a few examples of the relations, and which we come across very often, okay, and which may or may not have these properties. Okay, of course, for a relation you need a set. Okay, you should have to start with some non-empty set and then define some relations on that. Okay, so let us start with the most familiar set. Let us say I take this set Z, set of all integers. Okay, you have seen this. Okay, and the relation is, okay, I will say that suppose you take two elements x z, that is two integers x, y and z. I say that x is related to y, you consider the difference x minus y. Okay, if that difference is divisible by 3, we say that x is related to y. Okay, now this is a very well known relation, it is called x is equivalent to y modulo 3. Okay, you must have heard of this term. Okay, we say that x is same as y modulo 3, but let us not use that term. I will simply say this, that is x related to y, this means x minus, okay, this means x, okay fine, x minus y is divisible by 3. X minus y is divisible by 3. Okay, all right. Okay, now what are the properties that this has? Can we say that it is reflexive? X minus x is 0, it is obviously divisible by 3. Okay, is it symmetric? Because x is related to y means x minus y is divisible by 3, and y is related to x means y minus x is it. So if x minus y is divisible by 3, obviously y minus x is also divisible by 3. Okay, so it is symmetric also. Is it transitive?
Yes.
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 Yes, sir. Oh wow, sure.
Yes.
Yeah.
And what is the argument here?
Yes.
Add.
Suppose you take three integers x, y and z, okay, and say x minus y is divisible by 3, okay, and y minus z is divisible by 3. Okay, yeah, then just add. So x minus z is nothing but x minus y plus y minus z. So you have sum of two multiples of 3. Okay, right? So it's a transitive also. Okay, that means it is an equivalence relation. It is an equivalence relation. Okay, so you can say that this R is an equivalence relation. Equivalence relation. Okay. Is it also antisymmetric? Why? Why?
-3 थे -6 को इक्वल थोड़ी है.
नहीं है.
Yes.
3 minus 6 was divisible by 3,
But not equal.
Right.
Big one.
3 is related to 6, 6 is related to 3, but they are different elements, right? Okay, so it is not antisymmetric. In fact, a relation cannot be simultaneously symmetric and antisymmetric, right? That's clear to you? Okay. Okay. Now you would have heard of this property of an equivalence relation, that every equivalence relation on a set partitions the given set into what are called equivalence classes. Okay, and what is this partition? That is, if you take any two equivalence classes, they are disjoint. Okay, they are disjoint, and their union is the whole of X, okay, that is what is called partition, okay. So let us just recall that fact. Suppose let us say, okay, forget about this example for the time being, okay. Come back to this general case. Suppose R is an equivalence relation on X, okay, and you take any element, let us say small x in X, okay. Then we define what is meant by an equivalence class containing X, okay, an equivalence class containing X. And we denote, usually the notation for that is this X placed inside the square bracket, okay, inside a square bracket, okay. That is called equivalence class containing X, okay. So, and what is that? It is defined as follows: it is the set of all y in X which are related to X, okay. Set of all those elements which are related to X under this relation R, set of all y in X such that X are y, okay, X is related to y under the relation R, okay. So you take all the elements which are related to a given element, and that forms what is called an equivalence class, okay. Alright. Now every element is in some equivalence class, okay. For example, X related to itself, okay. So if you take union of all equivalence classes, that has to be same as X, okay, union of all equivalence classes. So we can say this, okay, by the way, this is called equivalence class containing X, containing X. So what we can say is that suppose we take union of all these equivalence classes, and take this X in X, then that union is same as X, okay. But that is trivial, okay. After all, you are collecting all those elements which are related to a given element, and each element is related to itself. So if you take their union, that has to be the whole of X. There is nothing great about it, okay. What is important is that if you take two equivalence classes, suppose you take two elements, let us say you take two elements X and Z, let us say X, and suppose I take two elements in Z, and suppose I consider the two classes, equivalence class containing X and equivalence class containing, let us say, Z. The point is this: either these two classes are the same or they are disjoint, okay, right. Either these two classes are the same or they are disjoint. Or what is the way of saying that? It is basically same as saying that if you take their intersection, if the intersection is non-empty, then the two classes must coincide, okay. If the intersection is non-empty, then the two classes must coincide. That is what we want to say is this: if this intersection is non-empty, then X is equal to Z, okay. Alright, now let us just quickly recall the proof of this, okay. How does one prove this? Suppose intersection is non-empty, what does that mean? There is some element common to both, okay. Suppose we call that element Y, okay, right. That means Y belongs to the equivalence class containing X also, and Y belongs to the equivalence class containing Z also, okay, fine. So what does this, that means X is related to Y and Z is also related to Y, okay. But now use the fact that it is an equivalence relation, okay. So if X is related to Y, and first of all Z is related to Y implies Y is related to Z, okay, and then X is related to Y and Y is related to Z, that will mean X is related to Z, okay. If X is related to Z, it means that this element Z itself is in this equivalence class containing X, okay. If that is the case, anything related to Z is also related to X, so that should also be here, okay. That means all of this, whole of this equivalence class containing Z must be a subset of the equivalence class containing X, okay, and similarly the other way, okay. Similarly the other way, okay. So these two equivalence classes must coincide, right. So coming back to what I said earlier, if you take the set of all equivalence classes, if you take the set of all equivalence classes, that leads to a family of subsets of X which is a disjoint family, okay, and its union is whole of X. Okay. Such a family is of any set, such a family of subsets of any set is called a partition of that set, okay. So what we have proved is that an equivalence relation on a set X leads to a partition of that set into a family of subsets, and each subset in that family is an equivalence class under the relation R, okay. And usually there is a fairly standard notation for this, that set of equivalence classes, okay, this is denoted usually by this X quotient R, okay. Usually that is called quotient set, okay. That is, if you take any equivalence class and consider the set of all equivalence classes under relation, that is called a quotient set, okay. And this is something that you come across very often in mathematics. See, sometimes you want to define something on this quotient set, okay, then you define something using one of the elements, then the usual problem that you run across is to prove that that is a well defined thing, okay. For example, suppose I want to define something about this equivalence class X, and I define it in terms of X, okay, but X is just one element in the equivalence class. Suppose you take some other element, the definition may change, so you will have to show at that time that that does not happen, and that is what you come across many times in mathematics. You will come across such situations, such proofs, okay. Alright, now let us go back to this example, okay. Let us go, okay. Alright, let us say, suppose I consider the equivalence class containing 0, okay, equivalence class containing 0. What are the elements in this? Okay, all multiples of 3, that is 0 plus or minus 3 plus or minus, okay. So you can, okay, let us say all elements of the form 3z, okay, okay, alright, okay. All right. Suppose I take equivalence class containing 1, so it have 1, 4, 7, minus 2, etc., etc., okay. So can you describe it like this? It is 3z plus 1, okay, all elements of the form 3z plus 1 where z is an integer, okay. So this is all elements of the form 3z plus 1 where small z is an integer, okay. Alright, and what about equivalence class containing 2? Again, I mean 2, 5, 7, again we can say that this is nothing but set of all integers of the form 3z plus 2 where small z is an integer, okay. Alright. What about equivalence class containing 3? That will be same as this, okay. So you are similarly, then if you take equivalence class containing 4, that will be same as, so there are no more equivalence classes, right. There are only 3 equivalence classes, okay. There are only 3 equivalence classes. So if I want to write this set X by R, now in this case let us say Z by R, okay, this has only 3 elements, equivalence class containing 0, okay, and you may have come across, this is usually denoted by Z3, Z suffix 3, okay. Have you come across this notation? Z suffix, usually it is popular in group theory, okay, Z suffix 3, okay. I will give you another example as an exercise, okay. Whatever we have done about this example, similarly check for this, okay. Okay. Let us now take the set R, okay, and I say that X, okay, instead of writing using letter R, see for the equivalence relation this is a usually commonly used letter, okay. When the relation is an equivalence relation, to denote a relation this is the usually used relation. So for example here also we will have something like, so quotient set will be denoted like this, X quotient this equivalence relation, alright. So what I will do is what I will define is as follows, okay. Take two real numbers x, y in R and say that x is related to y, this means, okay, suppose this means sin x is equal to sin y, okay. Okay. Now I will not indulge into any further discussion in this example, take this as an exercise, okay. Exercise is that check whether this is an check whether this is an equivalence relation okay, and if it is describe the set, describe the quotient set, just as here we have given the exact description of the quotient set, okay. Here there are exactly 3 elements, okay. If that is an equivalence relation, you give a similar description of all equivalence classes under that relation, okay. How many are there and whether we can identify with some well known set, etc. Okay. See why we talk about this quotient set, in many cases this quotient set can be identified with some well known set, for example as I have said here, okay, this can be identified with a well known object z suffix 3, okay. Alright. Okay. Now let us go to some other examples, okay. This time I will change the set and I will call this, okay, I will say suppose you take this is, let us say example 1, just so that we can refer to it later if we need, okay. Then let me take this as example 2, I take the set as set of all natural numbers, okay, and yeah, natural numbers means, as you know, the numbers 1, 2, 3, etc. Okay. So suppose we take say 2 such natural numbers m and n, okay, then I should say what is meant by saying that m is related to n, okay. Alright, I say that m is related to n if m divides n, understood, okay. So for example 2 divides 4, so we say that 2 is related to 4, okay. 2 does not divide 5, so 2 is not related to 5, okay. So that way, okay, so we will say m is related to, so I will say that this m or n, this means m divides n, you are familiar with this notation, m divides n, okay. M divides n means what, there exists a natural number, let us say k, such that n is equal to m times k, okay, that is the meaning of m divides n, okay. Okay. Now what about this, is this yeah, okay, this is first, okay, let us see one by one. It is symmetric, sorry, it is reflexive, okay, because given n it divides itself. Is it symmetric? No. Obviously not, okay, because if, and what is an example, m divides n and n does not divide m, fine, okay, so it is not symmetric. Is it transitive? So m divides n and n divides some p, that will imply that m divides p, right, okay, that is easy to see, okay. Is it antisymmetric? Right, if m divides n and n divides m, that is if n is equal to some k times m and m is also equal to some say t times n, then the only way in which this happens is that number k must be 1, okay, so in which case m and n must be same. So this is the example of what we have called partial order, okay. Okay, we shall see some more examples because these are the ones which we will come across very often and need also very often, okay. Let us say this is example 3. In this case I take x as any non-empty set, okay, and we take the set of all subsets of x, okay, right. Now this is something we will need very often. So let me use this standard notation. There are two notations followed for this. Okay, it is called power set of x. Either you use this notation, power set of x, or another popular notation is this 2 power x. Okay, there is a reason for this notation. We will come to that little later. Okay, but these two notations are used fairly common for denoting set of all subsets of a given set x. Okay, so I am going to define the relation not on x but on this power set of x. Okay, power set of x. So what are the elements here? Those are subsets of x. So suppose we take, let us say, two elements. Suppose I call those two elements a and b. They are in. I will use this notation 2 power x. Okay. And we use the usual subset relation. Okay, okay. So we will say that a is related to b if a is subset of b, subset or equal to. Okay, either it, I do not say proper subset. Okay, it can be equal to. So a is we say that a is related to b if a is contained in b. Okay. Now what about this? Each set is contained in itself. Okay, a is a subset of, so it is reflexive. If a is contained in b and b is contained in c, a is contained in c, that is fine. If a is contained in b and b is contained in a must, okay, right, and it is certainly not symmetric. Okay. So it is also an example of a partial order. Okay, all right. Okay. I will take one more example, example 4. And this time I will take the set as set of all real numbers R. Okay, all right. And suppose you take two real numbers x and y. Okay, I will take the usual less than or equal to, okay, order. Okay, we say that x is related to y if x is less than or equal to y. Right, if x is related to y, if x is less than or equal to y. Okay. You can say again this also is reflexive and antisymmetric and also transitive. Okay, so this is also an example of a partial order. Okay, it's also an example of a partial order. Okay, all right. Now let us proceed further. If a set on which a partial order is defined, that is called a partially ordered set. This is the standard terminology for this. Okay, it is called PO set, that is partially ordered set. Okay, that means a set on which a partial order is defined. Okay, all right. Okay. Now suppose R is a partial order on x. Okay. Now we want to define one more concept related to partial order. Suppose you are given two elements x and y in x. Okay, then for a general partial order, or not only for general partial order, for a general relation, okay, we are not saying that any two such elements must be related to each other. Okay, given any two arbitrary elements, there may be no relation. Okay, okay, it is not necessary that either x are y or y are x, etc. Okay, but suppose it is a partial order, and suppose that is true, that given two elements x and y, either x is related to y or y is related to x. If that happens, then we say that that is a total order. Okay, that is a partial order is said to be a total order if given any two elements, either x is related to y or y is related to x. Okay, so let me just say, so we will say that R is said to be a total order, said to be a total order if for any given x and y in x, x is related to y or y is related to x. It cannot happen that x and y, that is neither of them is related to other. Okay. In general, when two elements are given in a partially ordered set, and if they are related to each other, we say that those two elements are comparable. Okay. Given a partial order, we say that two relations are comparable if they are related to each other. Okay. So this is a term used. Okay. So in a general partially ordered set, given any two elements, they may or may not be comparable. Okay. There may be no relationship between the two. Okay. But in a totally ordered set, any two elements must be comparable to each other. Okay. Any two elements must be comparable to each other. Alright. Now look at the examples of partial orders which we have discussed here, okay, and see what is true. Okay. Which of them are total orders? Look at this first example here. Yeah, that is last example. Okay, that is if you are given two real numbers, then either x must be less than or equal to y or y must be less than or equal to x. Okay, so that is an example of a total order. Okay, that is an example of a total order. Okay, but suppose you look at the first example. Suppose you take, let us say, elements 2 and 5. Okay, suppose you take elements 2 and 5, then neither 2 divides 5 nor 5 divides 2. Okay, so these two are not comparable at all. Okay, these two are not comparable at all. Okay, so that is not a total order. Similarly, this example, you can easily find two sets A and B, two subsets A and B of x such that neither is contained in the other. Okay, right? Okay, so total order is something much more extra than the usual partial order. Now it can happen that in a partially ordered set you can find a subset which is totally ordered. That is always possible, right? For example, in this, okay, this itself is not a totally ordered, this is not a totally ordered set. Okay? But suppose I collect this set, let us say 2, 4, let us say 2, 4, 8, 16, etc., etc. Okay, or okay, fine, we can just stop here. Okay, 2, 4, 8, 16. Okay, though the original set is not totally ordered set, okay, this subset is a totally ordered set, right? So it can happen that in case of a partially ordered set, you may be able to find subsets which are totally ordered. Okay, so such subsets are called totally ordered sets, or there is also a very popular name for them. They are called chains. Okay, so chain is a totally ordered subset. Chain is a totally ordered subset. Let me again repeat, a given partial order may or may not be a total order. Okay, but that partially ordered set may, in fact usually it will contain subsets which is totally ordered, so such subsets are called chains. Okay, all right. Okay. Now it is fairly common because of the popularity of this particular order. Okay, usually total orders or partial orders, they are denoted by this symbol. Okay. Now we shall use some again standard terminology. We shall say that, okay, let us say that I will say that this is, let us say this is a set X, let X be a set, and I will denote this as a partial order on X. Okay, X be some non-empty set, and this is a partial order on X. Okay, of course I tell you that you should not confuse this, though I am using the same symbol. It is not that less than or equal to, it can be any partial order. Okay. Then suppose we take a subset, let us say A is a subset of X. Okay, we say that this subset A is bounded above with respect to this partial order. Okay, if there exists some element such that every element in A is less than or equal to that element. Okay, right? Okay, we will say that A is said to be bounded above. Said to be bounded above if, okay, let me give some name to that one. If there exists some element, let us say m in x, there exists some element m in x such that a is less than or equal to x for every small a in a. Okay, a is less than or equal to x for every small a in a, and this is a term that we are defining. And this element m is called an upper bound of a. Okay, this element m is called an upper bound of a. Okay. So a should be less than or equal to m. Thank you. A should be less than or equal to m. Okay, and m is called upper bound of a. Okay, upper bound, a standard short form uses ub for upper bound. Okay, all right. Then we shall continue with the properties of this upper bounds and similarly lower bounds, etc., and what happens to this bounded sets in a partially ordered set, etc., in the next class. Okay, we will stop with this for today.